For question number 31, we're going to use a known power series and do a substitution and integrate that power series expression so that we can evaluate the integral from 0 to zero point 0.2 of x log 1 plus x squared. So some of the known power series, we have our basic power series, our geometric, infinite geometric series, which is x to the n, where the function is 1 over 1 minus x. The other one that we have is that one that we're going to use is the ln of x plus 1, and it's going to be x to the n plus 1 over n plus 1, and it's an alternating series, so it's negative 1 to the power n. So that's one we're going to use because we have this ln x expression. So the first thing I'm going to do is I'm going to express that the log expression as a series. So I have that outside part here. I've got that extra x here on the outside, so I'm just going to express that as x like that. And that's from 0 to 0.2. And then we have our series part of this. So we're going to start at n equals 0 to infinity. We have negative 1 to the n. And then we're going to have this part of our series. So we have the n plus 1. And in the numerator here, we have this x to the n plus 1. But instead of just x, we've replaced this with an x squared. So we've embedded an x squared in there. So there's my series that represents the original function. And I'm going to just rearrange this and simplify it so I can integrate this a little bit easier with the power rule. So that x on the outside, that needs to come inside. From n equals 0 to infinity, negative 1 to the n, alternating. That power on x, so we're going to end up with x to the power 2n plus 2, but we have that extra x, so we're going to end up with a plus 3. So that x, that plus 3 includes that x that we had on the inside there. And then we're going to integrate this expression. So integrating this, we're going to have negative 1. Negative 1 to the n. We're going to have the n plus 1 outside the integral as well, because we don't need to integrate that. We're now just going to apply the power series to the x power. So we're going to have x to the power 2n plus 4. Increase the power by 1, and we're going to divide by 2n plus 4. So in the denominator, we have these two factors, and we're going to do this from 0 to 0.2. So we need to get 6 decimal places of accuracy. So I'm just going to write out my expansion. So I have n equals 0, n equals 1, n equals 2. So when n equals 0, I plug 0 in, I'm going to have positive 1, n over n plus 1 is 1, and the x part of this becomes x to the power 4 over 4. The next term is going to be negative. When n equals 1, I'm going to get negative. It's going to be 1 over 2, so I get 1/2 in the denominator. In the other denominator, I'm going to end up with 2 times 1 plus 4, which is 6. So I have 2 times 6, which is 12. Okay, so the 2 is from the n plus 1. The 6 is from the 2n plus 4. And then we have x to the power 6 here. Plus, when we plug this in, we're going to end up with x is 2, so we're going to end up with positive 3 times 8, that's going to give me 24. Okay, so we have x to the power of 8. So that's going to be x to the power of 10 minus, when n is equal to 3, it's going to be, in the numerator here, it's going to be x to the power 3 times 2 plus 4. That's going to be 10. Oops, I think I've got this one wrong here. This one is 8. This becomes x to the power 10. And in the denominator, we're going to have 3 plus 1 is 4 times 10. So it's going to be 40. And we can do more ... But we're going to integrate this from 0 to 0.2. Now, I'm pretty sure that we can do this within the 4 terms. So I'm going to do some calculations here. I need to get 6 decimal places of accuracy. So when I calculate n equals 1, I get and plug my bounds in. My bound of 0 is just going to be minus 0. So I'm just going to plug in my 0.2. When I do those calculations, I get 0.0003966. So that's the first 7 digits. When I plug it into the first 2 terms, when I plug it into get a partial sum of the first 3 terms, or when n equals 2, I get 0.0003947. It just keeps on going. When I do it into n equals 3, the first 4 terms, I get 0.0003947. And already when I'm looking at my 7th and 8th decimal places, they seem to match. So I've got my accuracy to my 6th decimal place, so I'm going to then determine that to the 6th decimal place, when I round it, my answer is going to be, the area under that curve is going to be 0.395. Okay, so that's the value of that definite integral by using a power series for log, rearranging that series so I can integrate it, applying the power rule, generating terms for that expansion, and then integrating with enough terms to give me the degree of accuracy that I need.